All right, so welcome back. But one more example here, we're finding the slope of a curve. This time we want to find the slope of our curve r equals 1 plus 2 sine 2 theta at two different points here, 3 pi over 4 and at 2, 5 pi over 12. Okay. So this time, instead of trying to work out my derivative like I did earlier by just looking at the xy functions, because my function's a little more complicated this time, I'm just going to leverage the stuff I had before. So with that in mind, I need to know what r prime looks like. R prime would be the derivative of this, which would be 2 times cosine of 2 theta times 2, or 4 cosine of 2 theta, or cosine of 2 theta. And then I'm just going to bring my formula from up above. Again, that I derived earlier. And I'm just doing this just to simplify the writing a little bit. Again, we can set up the x and y's like we did, and that still works. But this time I just want to use this formula here because I think it's just a little bit simpler and a little quicker. But again, there's nothing that says you have to use a formula. You could, again, set up your x and y functions and proceed that way as well, and that's perfectly fine. Okay, but I'm just going to set it up with the functions time since I have it at my disposal. And so that's going to be f prime times sine. So 4 cosine 2 theta times the sine plus f, this stuff, times the cosine. So that would be plus cosine theta plus 2 sine 2 theta cosine theta. That'll be on top. And then on the bottom, it's going to be f prime, 4 cosine times cosine. So 4 cosine 2 theta times cosine. And then minus this stuff times sine. So that'll be minus sine theta, and then minus 2 sine 2 theta sine of theta. Okay, and then we want to look at our points of interest. Okay, and so at the point 3 pi over 4, so all that matters here for the derivative is the angle, not what the radius currently was at that point. So we plug in pi over 4 for our dx dt, or dy dt, sorry, dy dx, get it right here eventually. Theta equals pi over 4. And then you could maybe go through and start piecing some things together here, or maybe opting not to. That's kind of up to you. Let me just show you, first of all, at pi over 4, the cosine 2 theta terms. That's cosine of pi over 2, so that's completely gone, and that's completely gone. Sine of 2 theta at pi over 4, sine of 2 theta is 1. So both of those things are going to be 1. And so what you're going to have here on top is cosine of pi over 4, which is square root of 2 over 2. And then you're going to have 2 times square root of 2 over 2. So basically you're going to have square root of 2 over 2 plus square root of 2. And on the bottom, you're going to have another square root of 2 over 2 minus 2 times square root of 2 over 2, or minus square root of 2. So you're on top, you're going to have square root of 2 over 2 plus square root of 2. On the bottom, you're going to have minus square root of 2 over 2 minus square root of 2. In other words, you have the same thing in the top and bottom except for a minus sign. So it's actually going to be just minus 1. So the slope at that point at pi over 4 for this graph is minus 1. Okay. You could plug all the numbers in. I just went ahead and kind of worked it out. And then we can do the same thing at dy dx, evaluated around 5 pi over 12. Okay, 5 pi over 12. Plug all those values in. What's 2 of 5 pi over 12 going to be? That's going to be 5 pi over 6. Okay, so this one, unfortunately, none of the things cancel out. And so just to do things a little quicker on my calculator, 5 pi over 12. If we converted that over to degrees, we would multiply by 180 over pi. Right, and we see that that's 75 degrees. So using my formula, I'm going to do it with 75 because it's just quicker to type it in. So we would go 4 times the cosine of 150 times the sine of 75 plus the cosine of 75 plus 2 times the sine of twice the angle, that would be 150, times the cosine of 75. Okay, so that's my top, and I get that number there. Negative 2.8284, and so on. Okay, and then I want to compute that in the bottom. So in the bottom, it would be 4 times cosine of 150 times the cosine of 75 minus the sine of 75 minus 2 times the sine of 150 times sine of 75. And notice you also get another negative 2.2824, and so on. So if you were to actually take the whole thing, that top thing, divided by that bottom thing, you should get 1. It's very, very ugly, but they all work out to be the same top and bottom. So the slope of that line is 1. The slope of that tangent line is 1. And if we go back to the graph here, this thing completes a full period after 2 pi. Here we are, 15, 30, there we are at the 45. Pi over 4, you can see this point right here. And we can definitely see, yep, definitely negative slope. Again, we can't tell exactly what it is, but a slope of 1 kind of works there with that point. And then 5 pi over 12 is it 75 degrees? Is that right? So let's get our bearings here. 45, 60, 70. So we're looking at right here, at this point here, and apparently there, that has a slope of 1. And, okay, so that's what it is. And a slope of 1 as we're passing that point there. Okay, and so then you can look at what's going on here. It's kind of a neat little graph here. This actually gives me rose petals, except one of them. Several of them have been expanded and several have not. So kind of a weird looking shape there. But we were only looking at, again, just that pi over 4 there. And then again here at 5 pi over 12. Okay. All right. So just wanted to show you another example here with finding slopes. Another example here with finding slopes, a little bit more of a difficult equation. But just to kind of, again, just practice this process. All right, so there we go.